Welcome to the third lecture of Chapter 11. Today we are going to talk about phase changes and how that leads to the construction of a heating curve or a cooling curve, and then talk about the calculations associated with heating curves and cooling curves. So we're going to go ahead and get going. First bit, just a review of phase changes. We know the transition from a solid to a liquid is called melting, and from a liquid back to a solid is freezing. The transition from a liquid to a gas is called vaporizing or boiling or evaporating. And a gas back to a liquid is called condensing. We can also go directly from a solid to a gas. That is called sublimation. And the opposite that it doesn't have on here, going from a gas to a solid, this is called deposition. Sublimation, a good example of that would be like dry ice. Deposition, you won't really see like in nature outside of lab, really going from a gas to a solid. So when we go from left to right here, I want to point out that is an endothermic process. So going from a solid to a liquid or a liquid to a gas, that is endothermic. Because in order to change from a solid to a liquid, your substance needs to take in energy. Like if we think about, ice, if we have solid ice and we heat it up, right, the ice is allowed to absorb energy, then it will be converted into a liquid. And, going from a liquid to a gas, like if we think about, boiling water to make some pasta, right? We put our liquid water on the stove and we turn the gas on so that the liquid can absorb energy and turn into a gas. So these are all endothermic processes. This is a very common place where people get mixed up and they think, it's getting hotter. And a lot of times when we think about our reactions, like if we touch a reaction that's hot, then we associate that with exothermic, right? The reaction is giving off heat. And so people think, my liquid is heating up, right? Therefore, it's hotter, so it's exothermic. No. The way that you are heating up the liquid is that you put it on the stove, right? You input heat. So make sure that you've got these definitions of endothermic and exothermic straight for the phase changes. If your stuff is absorbing heat, that's endothermic. And if it's releasing heat, like going from a gas to a liquid, right? Your substance is cooling down. It's releasing heat. It's losing heat. That is an exothermic process. So make sure to pay careful attention to those with respect to phase changes. This is a really common place where people get tripped up over something like this. So the focus of today will be on constructing heating curves. So if we think about, what happens when we add energy to a solid. So if we have some solid ice and we, heat it up, what happens? The solid will eventually become a liquid, and the liquid then will eventually become a gas. And as the energy is added, right, the kinetic energy is increasing. Right? So we've talked about kinetic energy before when we were talking about gases, but it applies to solids and liquids as well. As your substance takes in heat, right, as it absorbs heat, the particles will move faster and faster and faster. So as your energy is added, right, as you add heat, your kinetic energy increases. So does your temperature. But our question here is, does temperature uniformly increase over time? Like if I start with some ice at negative 20 degrees and I applied a constant amount of heat, will that cause your temperature to go up at a steady rate? And the answer is no. It doesn't just continually increase. We have some instances where the temperature will stop increasing for a while, and this is when it changes phase. Okay, so the temperature will continue to rise until we finally reach the temperature at which the solid begins to melt. So while it's in the solid phase, as we increase the amount of heat, right, then your solid, say your solid was at negative 20, your solid will continue to get warmer and warmer and warmer until it hits 0 degrees Celsius. And so there's two temperatures that are really important for water, 0 degrees Celsius and 100 degrees Celsius. These are when we have the phase changes. So your solid will continue to warm up until it hits 0. When it hits 0, instead of the energy being used to make the solid particles move faster to increase their kinetic energy, instead of them being used for that, now your energy is going to be used to change the phase. So here we have, if we start here at -10, we increase heat, our molecules are moving faster and faster and faster and faster and faster, which is why the temperature increases. Remember, temperature is a measure of how fast our molecules are moving, essentially. But when it gets to 0, right now we know that ice melts at 0 degrees Celsius. So instead of the energy being used to keep making the molecules move faster, now the energy is being used to break the intermolecular forces. Right? We talked about that previously in this chapter. Say for water, we know water is held together by hydrogen bonds, which are very strong interactions. And so we now will use the heat being added to break those intermolecular forces or loosen those intermolecular forces, right? And so that will be what happens during the melting part. So now, even though we are still adding heat, the temperature does not change. The temperature is not being used to make the molecules move faster. It's being used to overcome the intermolecular forces between the molecules. And once it overcomes all of those intermolecular forces, right, we take all of our solid and turn it completely into a liquid. Then our molecules will have more space between them and the temperature can go back to rising, right? So we took our solid, we heated it up to 0, and then we allowed it to melt. We broke those intermolecular forces. And as soon as all of it is melted, and not until all of that ice is gone, but once all of it is melted, then the energy will be used again to raise the temperature. And the same thing will happen here. The molecules will move faster and faster and faster in the liquid phase until it hits 100. And then the same thing will happen. Once we hit 100 and our water starts to boil, now the energy being input is no longer being used to make the molecules move faster in the liquid phase. Now it will be used to break the intermolecular forces even further, right? Almost completely, and release those molecules to the gas phase. So that's why we're going to see a straight line again here at 100 degrees Celsius, because the energy is being used not to make the molecules move faster, not to increase the temperature, but to overcome the intermolecular forces that are holding them in the liquid phase and convert it to the gas phase. Okay, so anytime we have a phase change, whether it's melting or boiling, our heating curve will be flat for the amount of time that it takes for all of the solid to melt or for all of the liquid to boil. Okay, so during these phase changes, the temperature will remain constant. And you can actually, try this at home. If you went and boiled some water, right, even though you're continuing, you've got the gas on or the fire on or whatever's happening on your stove, right, even though you're inputting more heat, your water isn't going higher and higher and higher. It's not getting to, 130 degrees Celsius or whatever the case may be, right? It's going to stay at or just below 100 degrees Celsius during these phase changes, right? Boiling water is a phase change. And during these phase changes, we are always going to have two phases present. We are going to have here, we will have solid and liquid. And then when it's boiling, we will have liquid and gas. Okay. On these heating curves, just as a way to remember, if you have a sloped line, whether it's sloped like this for a heating curve or like going the other way for a cooling curve, that will always be a phase. Okay, so like solid or liquid or gas. When we have a flat line on our heating curve, those will be phase changes. Okay, so that's like melting, boiling, condensing, freezing, all of that kind of stuff. Okay, because the temperature will remain constant during the phase changes until we've completely changed phase. So this is what the heating curve looks like for water. So I just have arbitrary, top and bottom temperatures. So I made this from -25 to 125. We just need it to go past 0 and 100. So below 0, right here, all of this is our phase 1. We will have ice that is warming up, but it will stay ice until it hits 0. And once the temperature gets to 0, right, that melting point, now our temperature will stop rising, and we will have, our temperature will stay flat because the energy is being used to change phase. But once all of it is melted, then the temperature will go back to rising, and it will rise again until we hit 100. And then once we hit 100, again, the energy being added is not being used to warm the water anymore. Now it's being used to change the phase. And so now we will turn it into a gas. And once it's all turned into a gas or turned into vapor, then the temperature will be allowed to rise again. Okay, so I need you to be able to draw these graphs for water or draw them for any substance and explain what is happening at the different points in the graphs. Again, remember, sloped lines are always going to be phases. Flat lines are going to be phase changes. And the reason that we have different, so you might notice that we have different lengths of the lines. So we have this flat line for the melting is very different from this flat line for the boiling. And that's because of these numbers here. Okay, so our energy that it takes to melt a liquid is much smaller than our energy it takes to vaporize, energy to melt a solid is much different from the energy needed to vaporize a liquid. We need much more energy to turn liquid into steam than it does to turn a solid into a liquid. So that's the whole length of the line thing. So again, we're going to take our solid. The temperature will rise until it hits 0, then it will melt. And then once it, is all melted, it will rise, the temperature will rise again till we hit 100, and then it will boil or vaporize. And then once it is all gone, then the temperature will rise again into steam. Okay, so this is the heating curve for water. We are going to associate some calculations now with the different portions of these heating curves so that we can see, specifically how much heat do we need to add to make these temperature changes occur. So, specific heat. The specific heat of the substance is the amount of heat required to raise the temperature of 1 gram of that material by 1 degree Celsius. We have covered this already back when we did thermo. So this is abbreviated by the letter C, right? I think it's shown capital here, but it's a lowercase c. And each substance has its own unique specific heat. You're going to get very familiar with the ones for water, but they will always be given to you. The most common one that you're going to use is for liquid water, and that's 4.184 joules per gram degree Celsius. But again, you're always going to have access to it. And your delta T here is going to be T final minus T initial. Not as important with the signs in this particular chapter. Just keep an eye on the fact that, if heat is absorbed, make sure your Q's are positive. And if heat is being released, then your Q's are going to be negative. This will always be true if you make sure your delta T, is always T final minus T initial. But again, at the end, you can always just make your Q's negative or positive depending on which way your heat flow is going. So here's our heating curve for water. We have different calculations that we are going to associate with different portions of the curve. So if we look in phases 1, 3, and 5, okay. Oh, it's no longer advancing. There we go. Phase 1, 3, and 5, those are the ones that involve a change in temperature. So that equation that we were just talking about, Q equals MC delta T, we can use that particular equation for this, area 1, 3, and 5 when it is a phase. So this would be for, solid, liquid, gas. Okay, if you think about our phase changes, where it's, here melting and boiling, if we looked at the change in temperature, right, our T final minus T initial for those sections, you'll notice the temperature is not changing during those sections. So if we had, if we calculated our delta T, it would be 0. And if we plugged that into this Q equals MC delta T equation, then our Q would be 0. So no heat is being added or removed, which isn't true because if you look, during this time, heat is being added. So this would not be an appropriate equation for these phase changes, but it is what we are going to use for the phases. So you're going to use it when it is in a phase, solid, liquid, gas. Do not use it for the phase changes, though. We have a different equation for that part. Oh, so this is just talking through what I was just saying. Temperature does not change during those phase changes. We're going to use a different calculation anytime we have a phase change. So the equation that we are going to use for these phase changes has to do with the heats of fusion and the heats of vaporization. Okay, so when we have molecules in the solid phase, they are packed really closely. They have a very organized structure, and separating the molecules by breaking some of those attractions requires energy. We know that these attractions are really strong, and we talked about earlier, hydrogen bonding is a really strong attraction. We have weaker ones that are, dipole-dipole, London dispersion, but the energy it takes to overcome those attractions in the solid phase, so this will be from, when we go from solid to liquid, we are going to use the heat of fusion, also abbreviated delta H fuse. Okay, and so that's for solid to a liquid. Similarly, we have molecules, when they're in the liquid phase, they're close together. They're kind of loosely organized, but molecules in gas phase have absolutely no structure and are really widely separated. So we have to completely overcome all of the intermolecular forces to go from the liquid to a gas. And to separate the molecules that much takes a ton of energy. The heat of vaporization, so going from a liquid to a gas, requires a ton of energy. So the delta H vape is commonly how this is referred to, is usually much, much larger than the delta H fusion. So like for water, this one is 6.01 kilojoules per mole. And, for water, this is 40.67 kilojoules per mole. So yeah, it requires some energy to melt the solid into a liquid and overcome those attractions. But since we're just kind of loosening the attractions and not breaking them completely, it's not as much energy as going from a liquid to a gas, where we're totally freeing those molecules and they're now going to be able to move independently of each other. So let me see. Oh, hang on, guys. There we go. All right. So for a pure substance, each phase change has a specific enthalpy change per mole. So that's that delta H vape, delta H fuse. So when we are melting, we'll use the heat of fusion. And for vaporization, we'll use the heat of vaporization. Okay, the heat of vaporization will also be used, just its negative value, when we are condensing. Okay, so it's going to be the same value, it's just now going to be negative. And for the delta H fusion, this will be the same value we will use for freezing. But again, it's just going to be negative when we go that way because we are removing that heat instead of adding it. And so then you've got some examples down there. The larger the intermolecular forces, or the stronger the intermolecular forces, the larger this delta H vape will be, because the more energy it will take to change from the liquid to the gas, right? More energy will need to be input to overcome stronger intermolecular forces. So we can, associate those. So like if you look, diethyl ether, this is a polar molecule held together by dipole-dipole interactions. And it has a fairly high boiling point as far as, small hydrocarbons go. So we've got their boiling point and then, the delta H vape, right, or heat of vaporization. But if we compare that to water, which we know has hydrogen bonding, which is stronger than dipole-dipole interactions, we have a higher boiling point and a higher enthalpy of vaporization. It will take more energy to overcome the hydrogen bonds than it will to overcome those dipole-dipole interactions. So here's some heats of fusion and vaporization for some common substances. If we look all the way to the left, we've got argon. Argon is a noble gas. It will only be held together by dispersion forces. Similar, methane will also be held together by dispersion forces. Both have very low heats of fusion, heats of vaporization. But as we get, stronger, like diethyl ether will have dipole-dipole interactions. We have ethanol and water that have hydrogen bonding, and then mercury has metallic bonding, which we haven't really talked about, but it's a fairly strong type of interaction. As we see an increase in the strength of the intermolecular forces, we are seeing an increase in the heats of fusion and heats of vaporization, the enthalpy of fusion and enthalpy of vaporization. So that's just saying, that they do correspond to those intermolecular forces. All right, so I'm going to show you how to use these mathematically. So this, we can use our heat of vaporization, or, this is also the same way that you would do the heat of fusion as a conversion factor. So here's our example problem. Whenever we are going to talk about a phase change, okay, so this is how much heat is required to vaporize water at its boiling point. This is a phase change. And anytime you're going to do a phase change, you're going to use the equation Q equals mole delta H. Okay, so when we have phase changes, we'll use that one. The other one, Q equals MC delta T, that will be for just phases. So this is for our phase change. So we'll have Q equals mole delta H. Right now we have kilograms of water. So if we take our kilograms, we turn that into grams. That's 2580 grams of water. And now we can convert our grams of water into moles of water using our molar mass. And so when we do that, we get 143 moles of water. And so then we can find out our Q value. We can take Q is equal to, like I said, mole delta H. And I just leave this as a generic delta H. And you can use fusion or vaporization depending on, if you are in, going from solid to liquid, liquid to gas, or, backwards. So we have 143 moles. And our delta H value for vaporization is 40.7. You'll also sometimes see this as 40.67 for water. Here we just have it as 40.7. So we have 143 moles times 40.7 kilojoules per mole, and that will get us 5830 kilojoules. So that's our answer. So that's how we will do these calculations for the phases. I'm going to guess you're going to be pretty solid with the ones for the phase changes, since we're familiar with that equation already. So I'm going to show you some examples where now we start using them together. So like this one. This says how much heat in kilojoules is required to convert 79.8 grams of water from liquid at 11.3 degrees Celsius to vapor at 100 degrees Celsius. Now be very, very careful when you're reading these problems, because you want to see what it's actually asking. If you just looked at it real quick, you might see, two different temperatures. I'm going to subtract them and get my delta T. Q equals MC delta T. It's going to be all good to go. But you need to be careful because it says vapor. So it goes from liquid to vapor at 100 degrees Celsius. So not only are we heating it to 100 degrees Celsius, but we're also undergoing a phase change. We are going to change it from a liquid to a gas. So my hint to you is to always draw the graph first. And by a graph, I just mean like a real rough sketch of what is actually happening in the problem. So usually what I'll do is I will just make myself a little graph, and I will put the largest temperature and the smallest temperature that the problem talks about. So smallest temperature is 11.3 and the highest is 100.0. And then I asked myself, okay, does anything exciting happen for water happen between those temperatures? And by exciting, I mean, does it have a phase change? And we know that water changes phase at 100 degrees Celsius. So we need to keep an eye on this upper temperature. And so it says from liquid to vapor. So as it goes from 11.3 to 100, we're going to have a sloped line because we're going to heat up our water. And then when it gets to 100, because the problem says that it's going to be a vapor, we also need to go through and change the phase. Okay, so we're going to, first heat up our liquid to 100 degrees Celsius. And then second, we are going to change from a liquid to a gas. So I will always break my problems up like this. I'll draw a graph and then see how many different calculations I need to do. Please note, there is no cutting corners here. If it's got multiple sections to your graph, you're going to have to do multiple calculations. Because you have different specific heats and different enthalpies of vaporization and fusion for all of the different sections, you can't really skip steps or combine steps. So you're just going to need to do however many portions of the graph you have. That's how many calculations you're going to do. So let's go. I'm going to make this on the next page. So we've got 11.3 and 100, and we are going to take this, like that. All right. So for the first part, that is a phase. And we have a change in temperature. So anytime we have a phase with a change in temperature, we are going to use Q equals MC delta T. So our our M here, we have 79.8, this is from the previous page, grams of water. Our specific heat of water for the liquid phase is 4.184 joules per gram degree Celsius. Again, that was given on the previous slide. You're not going to need to memorize that at all. And then our change in temperature here, this will be 100.0 degrees Celsius minus 11.3 degrees Celsius. So when we subtract those, we get 88.7 degrees Celsius. And so I do that separately so I can keep an eye on my significant figures, because now if I look, I'm going to have 3 significant figures out of this calculation. So when I multiply all of these together, I get 29600 joules. And be careful, whenever you use Q equals MC delta T, because of this C value, our answer comes out in joules. When we use that Q equals mole delta H value, it's going to come out in kilojoules because of the delta H is typically given in kilojoules per mole. So be very, very careful. This particular problem asked us how much heat in kilojoules is required to do this conversion. So I'm going to convert this now to kilojoules. All right, so that's how much energy it's going to take our liquid water from 11.3 degrees Celsius up to 100 degrees Celsius. Now that it's hit 100 degrees Celsius, we need to change the phase. So we're going to take our water and we're going to turn it into a gas. So now, since there's no change in temperature here, this is a phase change, we are going to use Q equals mole delta H for this portion of the problem. So we need to take our 79.8 grams of water and convert that into moles of water. So that will get us 4.43 moles of water. And then we can plug that in to this equation. So we have Q equals 4.43 moles times our delta H value. And that was given on the previous slide as 40.7 kilojoules per mole. Then I can multiply those out. It comes out to 180, so make sure you put 180 point to make sure that you are, conserving all of your significant figures. So this should have 3. Now we have, how much energy it takes to raise the temperature of water to 100 degrees Celsius and the amount of energy it takes to convert the liquid water into steam. So now our last step would be to add them up and get our total. So we'll take our 29.6 kilojoules plus our 180 kilojoules, and we will get 210 kilojoules as our answer. Again, always be sure to round for significant figures. This one follows the, addition subtraction rule. So that's going to be numbers past the decimal point. So here we have one number passed, no numbers passed. So we're going to go with no numbers past the decimal point for our answer. So that would be how you do a multi-step problem. I have one more example for us. This would be how much heat in kilojoules is released when we lower the temperature of 12 grams of benzene from 25 to -10. So you're welcome to try this problem out on your own if you'd like, and then, come back if you get stuck or you want to see the answer. But I'm going to go through it. This is a 3-step problem, just as a heads up. But always draw the graph first and then do your calculations. So if you'd like to pause here and try it out, you can. Otherwise, I'm going to go through the answer. All right, so how much heat in kilojoules is released to lower the temperature of 12 grams of benzene from 25 to -10? So again, first thing I always do is draw the graph. So we've got our graph here. I put my lowest temperature at the bottom, -10, and 25 will go at the top. And then I ask, is there anything interesting that happens for benzene in between? So be careful, this is benzene, not water. And we don't know as much about benzene, but luckily we have all of this stuff in this table. And it says, here we've got our melting points and our boiling points. So our boiling point is outside this range, but our melting point falls within the range. So our melting point is 5.5. So we know that this is going to have a flat line at 5.5 degrees Celsius because that is when our substance is going to melt. And since it is cooling down, right, we're looking for how much energy is released. It's going from 25 to -10. This will be a cooling curve. So our graph will go in the opposite direction that it did previously. So we're going to have 3 different sections to our graph. We're going to have our liquid benzene, then we're going to freeze it, and then we're going to have our solid benzene. Okay, and then once we get all of our answers, we're going to add them all up to get our total. And again, we're going to solve for this in kilojoules. So let's try this out. I'm going to copy that graph up here. We had 25, and we had -10, and 5.5. And this was a cooling curve. And we had 3 sections to our graph. Okay, so for our first section, we have a phase, right? We have a change in temperature. We are taking our liquid benzene and we are cooling it down to its freezing point. So again, 2 different ways you can do this. You can, do your T final minus T initial, and that will get you your negative numbers, and you can add all your negative numbers all the way through. Or if you'd like, you can do it all positive and just switch the sign to a negative at the very end. I don't care. Either way is fine. Just make sure your final answer ends up negative or positive as it's supposed to be. So our first step will be to do our Q equals MC delta T because this is a phase change. This is a phase, not a phase change. We have a change in temperature. So we have 12.0 grams of benzene. And if you look at the previous slide told us that the specific heat for liquid benzene is 1.70 joules per gram degrees Celsius. And then our delta T value, we are going to do T final minus T initial, so 5.5 degrees Celsius minus 25.0 degrees Celsius, and that will get us negative 19.5 degrees Celsius. Okay, so again, out of this, we're going to get 3 significant figures. So Q equals, when we multiply all of those together, negative 398 joules, but our answer needs to be in kilojoules, so we'll go negative 0.398 kilojoules. So that's our answer for part 1. The second part is going to be a phase change. We're taking our liquid benzene and we are converting it into solid benzene. We're freezing it. So here we're going to use Q equals mole delta H. So we'll take our 12 grams of benzene, and it had on the previous slide that our molar mass of benzene is 78.11 grams per mole. So we'll go ahead and convert our benzene into moles, and we get 0.154 moles of benzene. So then we can go Q is equal to our moles times our enthalpy of fusion. Remember, we're going to use fusion when we're going from solid to liquid or liquid to solid. But here, since we're going from liquid to solid, we are going to make it negative. Okay, so now we've got 0.154 times negative 9.8 gets us negative 1.5 kilojoules. Again, make sure to pay attention to significant figures. We should have 2 out of this calculation. And then lastly, our step 3, we're going to take our now frozen benzene and cool it down to negative 10 degrees Celsius. So again, we're seeing a change in temperature, right? This is a phase, so we're going to use Q equals MC delta T. So Q, and we've got our same 12.0 grams, but our specific heat is different now. We need to use our specific heat of a solid instead of the one for a liquid that we used earlier. So this is 1.25 joules per gram degrees Celsius. Our change in temperature here, we are going to go, our final temperature minus our initial. So we'll have negative 10.0 minus 5.5. So this is negative 15.5 degrees Celsius. So when we go through and we multiply all of that out, we get negative 233 joules, which is negative 0.233 kilojoules. And then finally, don't forget to add them up at the end, right? People get to here and they're like, oh, okay, I'm done. I've done steps 1, 2, and 3. But you need to actually answer the question. You need to find the total value. So we're going to add them all up. Negative 0.398 plus negative 1.5 plus negative 0.233 will get us negative 2.1 kilojoules. Okay, be careful again. Following our addition subtraction rule, this will be numbers past the decimal point. We've got 3, 1, and 3, so we go with 1 past the decimal point in our answer. So that will be how you do these big multi-step problems. Again, make sure, the key here is to always draw the graph and to know what is really going on and how many different, sections and calculations you will need to do. And then, like I said, make sure to add them together at the end. So that's end of today's lecture. Please send me any questions you have, and I will see you guys next time.